Welcome to an EdgeFactor virtual workplace experience. Today, Mark talks to us about his work as a project manager at Ameritech Die Mold. We'll be looking at the following chapters. Chapter 1, Ameritech Company Overview. Chapter 2, what is a plastic mold? Chapter 3, what is a 5-axis milling machine? And finally, Chapter 4, what is a sinker EDM? Let's dive in.
Hi, my name is Mark Rotman. I'm from Ameritech Die Mold, and today we want to kind of show you how intricate plastic parts are made. So I don't know if you've ever thought about it, but you interact with plastic every day. Somewhere, somehow, there was an injection mold that made it. And we want to talk a little bit today about how injection molds are produced and what it takes to actually make those parts. So if we look around on this table, we've got a bunch of different examples. So a lot of our industries, we focus on the automotive industry. So this is a driver's side airbag cover. I'm sure you're familiar with that. And then for those that don't like to do dishes, we have appliance industry. So we do work for the dishwasher. Then we get into some consumer goods. So this is a lid for a battery box and some various consumer goods here. So we have a tape case. This one's very interesting because you'll notice there's two different colors. So these are two different plastics that are injected into this mold that form the harder substrate shell and then the softer, what you feel, the softer rubber, the TPO we call it. So it has different injection points, but these pieces go together and form a tape case. So right now we want to show how plastic parts are actually made, and this is the final step after we've completed building the injection mold. So all plastic parts are going to start out as some form of pelletized version. So we have these natural pellets here, and what we're going to do is we're going to load these pellets into a hopper on our molding machine. So up on top we've got a hopper. So the pellets are going to fall down and get augured in using a screw, and they're going to pass several heating elements, and they're going to basically go from room temperature to about 430 degrees. So that's going to melt the plastic and turn it into almost a liquid, and then we're going to inject it into the mold at very high pressure. So if we come up here, we can see a part that's been recently molded. So the part is waiting, ready to be pulled off of the mold. So we can pull it off, and typically this would be done by a robot in a production environment. So once the part is removed, we're ready to close the machine and let it cycle another. So as the machine closes, it's going to have two different halves. So we've got what we call the cavity side, forms the front half, and then the core side on the back side. That's going to form all this back detail. So these two halves have to come together and perfectly align. If there's any misalignment, then we'll get a misalignment of the actual part. The part will be shifted to the side. And the other thing that's very important is that the part doesn't have any kind of gap that has to seal perfectly. We can leave a small amount of gap to allow air to escape the cavity, but maybe only 1/1000th of an inch. Anything more than that and plastic will leak out. So we'll see here the mold will open up, and we've now produced another part. So the time frame for this, for making these parts, is roughly 60 seconds. So again, we're going to take the pellets, we're going to go into the hopper, and they're going to go through a melting process. And as they're being melted, they're getting prepared to be forced into this mold where it'll take a pelletized version and turn it into an actual part. So what we have here is the injection mold. So it's two different halves. So right now it looks like a giant block. And the reason for that is when that plastic comes in, it's coming in at very high pressure. So this molding machine has to hold these two halves together with 500 tons of force. It's a lot of pressure to be able to withstand all that coming in and make sure that the two halves don't just pry open. So inside the two halves, we have this area that's been machined out of steel. And what that is the cavity impression. So you can see we can lay the part back up in here. So there's a gap inside this steel, we call it a cavity, where the plastic can enter and form that shape. So the core side is very special too because one, it forms the opposite, the opposing half, but its responsibility is also to remove the part from the tool. So the core side, its purpose is when the mold opens, it's going to eject that part out. So we have different features inside the mold that are going to advance forward and push that part out when it's ready. So we can stroke it forward here and show you. So after the part has been molded, it has to be forced out of that core side, and that's the purpose of all these features. So all these features are tied to a backing plate, so they all move together in unison. So the two halves will come together, the mold will clamp up, and then the next shot will be injected into there. And overall, it takes maybe 3 seconds to fill this part, and then the next 30 seconds are cooling. And then the rest of the cycle time is opening, closing, and ejecting the part out. So that plastic is going from 430 degrees back down to room temperature or slightly warmer so that it can be ejected out as a finished product, and then the cycle can repeat. So it's very fast. So what we actually produce here at Ameritech is the injection mold. It's everything inside of these two platens here. And the way we like to think of it is the molding machine is kind of like a cordless drill. So most people are familiar, cordless drill, you buy one size, put the battery in and can operate it. But the drill bit is what actually does the work. So with one cordless drill, you have an opportunity to utilize multiple drill bits. You can get different size holes, different features. We make the drill bits, but it's an injection mold. It's the tool that goes inside of the machine. So we've got the two different halves here. When they mount into the machine, we want to make sure that everything is located properly. So to reference it in the machine, we have one ring on the front side of the tool that locates it into the molding machine. And then on the back half, we have different features on the back side that have to tie in to make sure that this plate can operate. Everything else location-wise is handled within the mold. So when these two halves come together to gain our alignment, we have these pins. So there's a pin here and a bushing here. So as the mold's closed, that gets you close, make sure that everything is aligned. And then at the final stage of this very last little bit, we have these straight locks. So if you see on this side, we have a standing lock, and on the opposite side, we have the female side of it. So a female side of the lock. So that shape is meant to enter together and maintain alignment on the mold as it's seeing molding pressure. In addition to that, there's also these tapered surfaces inside the mold, and those are made so that it all helps lock everything together. So this taper surface has a reverse taper surface on the opposite side. And that way everything is locked in and very, very robust, because we don't want to have anything moving around during this process, because this process is very hard on the tool. So we have here another injection mold, and we're looking at the back half, the core side. So we'll notice again, we've got the different alignment features. We have the bushings and the straight locks, and then we have the actual core detail here that's going to form the back side. And what's interesting about this is when the two halves come together, they have to leave a gap, and that gap is where the plastic is actually going to fill. So this part is about 2 millimeters thick. So when the two halves come together, there's a 2 millimeter gap between this side of the tool and the opposite side of the tool. So it's very close fit together. And then around the actual edge where it seals off, there's no gap. It fits together. And the only gap that's remaining is the one that we'll intentionally leave for venting so that air can escape the cavity whenever plastic goes in. So even on this center here, the other half of the tool will have to come down and shut off against this top diameter. And then it'll have to form through these windows. So there'll be steel that has to come in here and seal off against this seal. so that when those two halves are together, plastic only enters the area it's intended to enter. And the other thing you'll notice is after the part has been molded, it no longer fits on here. So when we do the molding process, we're heating the plastic up, it expands, it gets larger. But as it cools down, it shrinks. So we actually have to build the injection mold larger than the final part, so that as it's molded and as it cures and shrinks down, the final part ends up the right size. So right now this won't fit back on there. But at one point, this part was molded off of this tool, so it fit perfectly. So with the two halves of the mold, the plastic actually has to get into the cavity somehow. So this is the cavity surface here. And what we have is some solenoids and different hardware, because the plastic's going to be coming from the machine on the front side, and it goes through a manifold system and actually comes through these small holes inside here. You can see there's 6 holes. And right now they're sealed up because they have a pin that's keeping it closed. And those pins can go open and close to allow plastic to enter from different points at different times. So if you look at the face of the part, you can see these same points. So there's one here, and here, all the way around the disc. So that's where the plastic actually enters the cavity to form the part. And again, that can open and close as needed. So maybe we want to have the plastic go one direction, and then we'll hold off on opening another gate until we want it to come out that side. So all of the components of the mold we're building out of various steel types. So our mold base we're making out of a tool steel. It's going to come in as a giant block of steel, and then we're going to have to begin whittling away the different shapes. So in this machine up here, we're doing most of the rough, heavy cutting. So you can see down in here, we're mowing away with a large face mill, producing large chips. The machine requires a lot of horsepower, a lot of torque to get that material out of there as quickly as we can. So this is how we will prepare the block. And from here, we'll go into our finishing machines. So on our finishing side, it's more of a finesse. We're using smaller end mills and cutting tools to form the shapes. And we also begin to utilize different axes. So instead of just a 3-axis machine, now we have 5-axis. So in addition to X, Y, Z, now we can tilt and we can rotate the table so that we can reach various parts of the workpiece that we're machining. So you can see in here we have the workpiece set up in the center. Right now we're doing a little bit of semi-rough cutting, so we're milling out some pockets. But again, this machine has the ability to tilt up and rotate around 360 degrees. So in this machine, again, another 5-axis machine tool. The head has the ability to tilt and the table will rotate. So we're doing some drilling. These drills have the ability to push coolant through there at up to 600 PSI. So we have various drills here. So this is like a gun drill. So you'll see the holes in the end of it that allows that coolant to come through at very high pressure and evacuate the chip out the shank of the tool. The other importance of the high pressure coolant is as this drill is spinning, the coolant helps make the tool rigid. Otherwise the tool, as it's spinning around, could wobble and start flopping around. So the pressure inside of this tool actually creates the rigidity to keep it straight as we're drilling that hole in there through the steel. So what we're working on here is inside the injection mold, we have various cooling lines that are running water through to help control the thermals of the block, to help that plastic set up and help pull that heat out and take it away from the tool. So we want to put angled lines so that we can reach different areas. Another way to achieve this nowadays is with conformal cooling. So we'll see a lot of people doing a 3D printing operation where they do metal sintering. So we're going to go in and spot face an area on the block so we have a nice flat pad to be able to go in and enter with a drill. So after the pad is created, the drill will come in and create the angled hole. So you can see that high pressure coolant forcing those chips out of that hole. And we're doing a little bit of a peck drill. So it's going in and coming out just to make sure everything is clear. A lot of times we'll be drilling through cross lines, and the drills don't really like going through an interrupted cut. So we have to be careful that we don't break a drill inside those interrupted cuts. So in the tool and die industry, we want to show that we utilize a lot of 5-axis machine tools. And what that means is traditional machine tools are only going to be 3-axis. So we operate in X, a Y, and a Z. And those are our only movement methods. So there's ways we can set up in a 5-axis machine tool so that we have rotations of those axes. So now we can tilt our cutter, or we can rotate our table, so that it gives us additional degrees of freedom, so that now we can use shorter tooling that doesn't have to stick out as far. Because previously, if we're going down in a 3-axis method, our cutting tool has to be longer than our workpiece so we can actually reach everything. But if we can go to a 5-axis and tilt off center, now we can use a very stubby and rigid tool holder to get very close to our workpiece. It's very important for us in the tool and die industry because all of our molds have to be very precisely made. So the longer we hold our tooling out, the more cutter deflection we risk having. So we can see in this work center, we're able to reach a very tall workpiece, but we're picking down with a small cutter down at the very base of it. So by tilting that tool off axis, we're able to reach more with a shorter, stubbier tooling situation. So you can see the table is rotating, and that allows us to get to all the different sides, and the head is tilted on an angle. So these are various mold components that we've manufactured in our 5-axis machine tool. So these are for the fan project. So you can see this here is very tall. So again, to be able to reach down on the inside here, we want to utilize a cutting tool that comes in on an angle instead of sticking out that far and having any kind of deflection. When we come in at an angle, now we can use a very short, stubby cutting tool and reduce our deflection. And that allows us to get a much more accurate cut and a better finish. So then even on the fan blade here. So in addition to the actual contour surface here that we machine, we also have drilled angled lines coming through each one of these fan blades, and that allows an area for air to escape. So we come in on the top here and it exits out the bottom. So it's coming in on an angle about like this. And that gives that air an opportunity to escape from the cavity and have somewhere to go. Otherwise, if we try to inject plastic in, it would be vapor locked. There'd be nowhere for the air to escape, and it would just try to compress the air. So right now we want to talk about a manufacturing process. It's called sinker EDM, electrical discharge machining. And this process is very unique because it's not like a traditional milling or drilling where you're using a cutting tool to form steel. In this process, we actually use electricity to erode away the steel in different images. So the way we do that is first we have to make what's called an electrode. So we can use various medias for electrodes. We have copper and we also have graphite. And what we're going to do is we have to take the electrode or the graphite from a blank state, and we have to machine down and whittle away that shape so that it actually looks like the part detail. And what that helps us with, if you take a look at this part here, this is a dishwasher basket that you may have seen. There's a lot of intricate shapes and structure here, all the different webbing to form this plastic part. And that's to allow water to be able to drain through there and not puddle in the bottom underneath your forks and spoons and knives. But if you think about what that detail has to look like in the steel, it's very intricate. And to form that with a traditional cutting tool, going in and milling all these slots would be very tedious. So we utilize the EDM process and we manufacture that shape in the graphite because graphite is much easier to machine. And when it comes in, we'll put it in the sinker EDM machine, and it'll come in and burn the steel. It'll plunge in, it'll get very close to the steel, and the electricity will jump off of it and erode away in that same shape. So that way the steel gets the reverse shape of what the part is. So when we inject the plastic in, it forms the part. So we have a lot of different applications here. We've got, again, we talked about the appliance industry. So we do a lot of dishwasher parts. Then you'll see here, this is a speaker grill that you would see in a car. We've done this is for a wheel hub, a hubcap. So I'm sure you recognize the logo. We actually had to use copper in this one because we wanted to use the EDM machine to do some polishing in addition to the burning of the detail. So after it was done burning, it could go around and orbit on the steel and actually rub a little bit of a slurry on the steel, so it would leave a mirror finish in the steel. Otherwise, all those little diamonds would be way too small to polish by hand. So all the graphite, we're gonna start out, we're gonna mount it on a work holding system so that we can utilize our automation and our robotics. But it's gonna start out as a blank of graphite. Then we're gonna use various cutting tools to come in and machine away to whittle away that shape. So we can see here in this milling machine, if we look through the window, it's currently manufacturing an electrode. So you can see it's cutting away that blank and leaving that shape in there. So we'll start with a very large cutter, remove as much of the mass as we can, and then we'll incrementally step down into smaller and smaller cutters. So starting out, maybe a 1/2 inch diameter, but then we'll get all the way down, let's see, to some of the smaller. This cutting tool is 10 thousandths in diameter. You can barely see the tip of it there. So that cutting tip right there is actually what machines away graphite. It's pretty incredible. So on this side, we have the actual sinker EDM machine. So first we talked about the graphite and the electrodes. Those are the cutting tools for the steel that we're gonna be forming inside the tank here. So we'll see everything is submerged under a dielectric fluid. It helps suppress any kind of fire and helps flush away the chips. So as we're using electricity, we're gonna be generating a spark, and that's what's gonna be burning away that steel. So we have 2 different sinker EDMs set up here. So we can utilize different workspaces, and all the cutting tools are shared in the middle here. So the EDM process is a little bit slow. So we want to utilize automation to hold different cutting workpieces so we can effectively burn through nights, through weekends when nobody's here. So right here, the robot's coming in to grab one of the cutting tools. It's going to swap out for a different electrode. And what it's going to be doing is burning the tip of this ejector pin here. So it's going to be forming a shape on the top of this ejector pin. So currently the ejector pin is flat. When it's finished, it'll have a contour on it. So the robot's going to grab a new cutting tool. It's going to come in, and then the tank will raise and begin to fill. Yep. So here we have the dielectric fluid that's going to submerge the workpiece and then also offer flushing. So instead of leaving a traditional chip like a cutter or a drill would leave, this leaves a dust, a debris. So the fluid will flush away that debris so it doesn't get in the way of the burning process. So the robot's loaded a new cutting tool. The tank is now going to fill. This cutting tool is going to get very close to the workpiece, but it'll never actually touch the workpiece. You want to maintain a gap so that the electricity has to jump across, otherwise it'll be in a short circuit. So the tank is going to continue to fill until the workpiece is completely submerged. And then the graphite will begin to plunge close to the workpiece. So now as it's plunging, each time it's down in the burn, electricity is jumping across. Then it raises up to allow that fluid to flush in, evacuate the chips, and then it plunges back down very quickly. So right now it's just roughing it down to the right size. Once it gets very close to the final shape, it'll actually start to orbit in a pattern to remove all that material to the final size. So right now it's kind of just roughing away the material very quickly. And that electrode will get some wear on it, so that's why we'll have to produce several electrodes for this burn. The first one will rough away the material, and there will be some amount of wear on the electrode, so we'll grab another one, replace it, and begin burning again and get it very close to finish size. And then a third one will come in and do all the final finishing to the final shape.